Alright, in this video I'm going to show you how to find natural frequencies of a truss, a 10 bar truss, as you see here. So this truss has 10 members, and horizontal and vertical members are 1 meter long, and the axial rigidity, or EA, modulus of elasticity times area of these members are the horizontal and vertical members, 4,000 kilonewton, and mass per unit length of them is 0.8 kilogram per meter. And diagonal elements, they have much smaller axial rigidity. It's 40 kilonewton, and their weight is negligible. We want to find natural frequencies and also mold shapes. Alright, so let's see how we could do that. Before starting, I'm gonna use, by the way, APDL, mechanical and cis mechanical, but before going there, we need to find modulus of elasticity, the right modulus of elasticity and area for our model. Alright, because this problem statement, we have rigidity EA, we don't have the the modulus of elasticity separately. So any combination of E and A's that are gonna that's gonna give us the product is equal to 4,000 kilonewton is gonna work. So let's see, we wanna pick one combination that works. So let me go to Excel first and find those properties. So for axial elements, E and A is, was it 40,000? Let me see, was it, yeah, 4,000 kilonewton, and mass per unit length was 0.8 kilogram per meter. So let's find the right E and A. By the way, mass is density, so rho times volume, right? So volume is A times length, and so that's mass. If I divide it by L, the length, L is gonna cancel, so mass per unit length is gonna be equal to rho times A. So density times area. So mass per unit length is rho times area. So alright, so material properties that I'm gonna need for a model analysis are modulus of elasticity, area, modulus of elasticity and density, and I'm gonna need area too. So we're gonna pick numbers for that are gonna provide, or gonna give us product of rigidity, or EA, equals to 4,000 kilonewton, and density times area equal to 0.8. Okay, so let's see what combination works here. So if I assume modulus of elasticity is okay, by the way, let me convert this to Newton. So 1, 2, 3. so standard unit. Alright, so let's say if modulus of elasticity is what? Is um, let's say 100 gigapascal or 100 right 100 give 100 times 1 to 10 to 9 Pascal. So let me write it in Pascal. So 100 giga means 100 and additional 9 zeros. 1 2 3 4 5 6 7 8 9. Okay, so this is modulus of elasticity in Pascal. So that gives me, since I have EA equal to 40,000, so my A is gonna be equal to, EA divided by modulus of elasticity. So my area in meter squared is gonna be this. Yeah, so if modulus, let's see, maybe if I pick something smaller, I'm gonna have my area being larger. So let's see, what is a good number we can pick that gives us a better M. Let me find the density, then we can play with that. Alright, so this is the area, and then the row density is gonna be the product is 0.8. So if I divide this by area that I found, is gonna give my density in kilogram per meter, right? So if we pick something smaller for E, let me right now is 100 E9, 100 gigapascal is giving these numbers. So if I have it instead of 100, 10 giga, if I have 10 giga, yeah, 10 giga, let's see. You see here I have 4,000 kilonewton. Let me double check. 4,000 and 0.8. Oh, I'm sorry. Oh yeah, okay, yeah. Diagonal element, okay. Yeah, so 4,000 kilonewton. I want to double check everything. So 4,000 kilonewton. So 4,000 and then actually a million, right? So if modulus of elasticity is let's see, 20 gigapascal, then I'm gonna have my area to be this and my density is gonna be this. Yeah, that's probably we can use these numbers. So you see, if I have modulus of elasticity this, area that, then my rigidity E times A is gonna be this 40, right? So the 40 4,000 kilonewton. So if I divide this by 1,000, it's gonna give me in kilonewton. So 4,000 kilonewton This is what the statement was saying, right? And then math per unit length is gonna be equal to A times rho. Sorry, so A times rho, sorry, A times rho is this times rho 0.8. Okay, so this is for the properties I'm gonna use for you know, for vertical members and horizontal members is gonna be this, and we need to repeat this for the diagonal members. So for diagonal members, let's look at it. It says that diagonal members weight is negligible, and then EA is 40 kilonewton. So 40 kilonewton means 40,000. Right? So it says weight is negligible. So if this guy, you see this one, is negligible. So I'm gonna put like a small tiny number here. Then if I use same modulus of elasticity, then area is gonna be this. We can use something like as not as stiff for that, maybe this much, or you know, 2 gigapascal. If I use 2 gigapascal, the area is gonna come out, it's like 10 times smaller than this one. Okay, and for density, I'm gonna use, for this problem, I'm gonna use a very small number, you know, so if you want this to be negligible, it could be very small number. So so area is gonna be this, and then density is gonna be very tiny number. That's gonna give me you know, rigidity EA of 40, and then density of this, you know, very small number. Alright, so this is just one combination that I found that works with this problem statement. You may find another ones. So I'm going to use this for to define my material properties. So let's go back to the problem and do that. Alright, so you come to open mechanical, answers mechanical, you pick structural, then you go here, element type, add, and you go here, link, element, activate that, so and then close. Alright, so you go here, material properties. As I said, I'm gonna define 2 material properties. So first one for the for the vertical and horizontal members. So let's look at here. I said modulus of elasticity, I consider this number. So let me copy paste it here. And then Poisson ratio, I don't need it. Density, let's come here. In SI unit is this. There you go. And then I'm gonna do another material. So new model, material number 2. So the modulus of elasticity, let's get this number. Let's see, come here, we can copy it here. Is that right? Yeah. That one was 10 times softer, so let me double check it. Like, the right number? Yeah, okay, so we have the right number there. And then that's modulus of velocity, Poisson ratio, I don't need it. Then density, let's come here. Density could be anything, a small number, because if I have a very small number, you know, it's gonna work. Something like very small number. I'm not putting 0 because if I put 0, that's gonna make the math 0. And then if you're doing model analysis, you have math 0, it's gonna give error in during the process, calculation. So I say okay, and then done. So material done. Let's define the sections. By the way, I have two sections. Section number one, the area is this guy. So the menu is hidden. You click on this, comes back. Okay, apply. Now section number 2, the area this time is this guy. Oh, sorry, so it's hidden, so you click on here. Yeah, so alright, so we have material 1, material 2, and then we have cross-section area 1, cross-section area 2. We could have kept, yeah, so, okay, yeah, let's go. So we need to now model the key points and the truss itself. So I say x in axis z, 1, 0, 0, 0. Number 2, 1 meter to the right. Number 3, 2 meter to the right. Number 4 is 0, but it's gonna go down. Number 5, okay, 1 meter ahead of it. And number 6, 2 meter ahead of it. Alright, okay, so these are my points. Now let's connect them. Straight lines. This to this, this to this, this to this, this to that, this to this. These are all the vertical and horizontal members. Then I'm going to connect this to this, this to this, this to this, this to this, and then cancel. Alright, so next I'm gonna do what? I'm gonna do meshing, right? So mesh attributes, we have to be careful. We have to keep pick lines, horizontal and vertical lines. For those guys, we're gonna use material number 1 and section number 1. Okay, that one we don't need to change. So then I'm gonna pick other lines, the diagonal lines, right? Pick diagonal lines for those guys. Section number 2, section number 2. Yeah, section number 2, material number 2. So okay, now I'm gonna mesh them. So size control, manual mesh, all lines. I want to just do one per member, one element per member. Okay, then I'm gonna mesh it. So analysis type, we're gonna do model. Okay, and then when I say model, then it says okay, how many frequencies you want to extract. Let's say I want to do 10, and then it's going to say, okay, what is the range you're interested? Let's say from 0 to 20,000. It's going to find 10 frequencies between those. Oh, by the way, let's see how many, you know, this model is not gonna have limited, you know, number of frequencies, so we may not be able to find 20. So too many could be too much, you know, this is what I'm trying to say. Okay, so let's define the lows, by the way. Especially I'm gonna limit this 1 degrees of freedom just to what happens in one plane, like in 2D natural frequencies and 2D mode shapes. Alright, so let's apply boundary condition. So these two guys, I'm gonna zero them, right? Everything zero. And let's look at this, by the way. I want to keep, as I said, I want to find frequencies and mode shapes only in plane XY, on plane X and Y, because just anything happening in 2D, not 3D case. So if you want to keep everything on 2D, you know what you can do? You can displacement, you see, you can come here and pick all lines, and we can limit their movement to XY plane. So the way I can do this, I can constrain any move in Z direction, right? Say all lines, whatever move you do, just keep them in XY plane. So this way, you see that? They are all locked, constrained. Okay, now we are ready to do the solution and look at the, right? Okay, so I come here, run it, solution done. So first we're gonna look at our results. These are our natural frequency. So 12.49, 36, 211, and so on, right? Okay, so the reason, as you see, we have only 8 of them. It didn't find up to 20. The reason is because if you constrain this model, let's look at it, to 2D, the degrees of freedom I have here is basically just 8, because I constrain node 6 and node 5, right? So no degrees of freedom there. But point 1, 2, 3, 4, these are the nodes I have, right? The only nodes I have are these 4 that are free to move. And on a plane, on XY plane, degrees of freedom of these 4 nodes, they're gonna add up to 8, right? So each of them can move either in X or Y. So number of degrees of freedom I have is 8. So that means that total number of natural frequencies I'm gonna be able to find in 2D is gonna be 8. Remember, I constrained the Z, movement is Z. So these are my natural frequencies. Yeah. And then next I'm gonna remove that Z constraint and see what happens. Alright, so these numbers are in Hertz, but that problem statement had natural frequencies in radian per second. So these are the same thing technically. Only the first 3 are listed here, so let's check one of them. You know, 12.49. Oh, let's do it in here. So equals 12.49 in Hertz. If I multiply it by 2 and pi, see how much I get? 78.47. See how much he has? Yeah, 78.5 rounded that. Alright, so the next one, 36, this guy, 36.48, 36.48. So let's go here. 36.48. Alright, so 229. Yeah, almost, right? So this is what we have. Alright, so we have it right. Now let's look at the mode shapes or dancing mode. To do that, since it's 2D, we can just look at it here and 2D. So I go Result Reviewer and let's look at those. Display structure and then mode shape. This is first mode shape. This is first mode shape. Okay, so if I do the second one, let me bring this back, stop it. We switch to second one. So what happened? Degrees of freedom. Alright, so this is slow. This is mode shape number 2. Mode shape number 3. Yeah, this is mode shape number 3. And mode shape number 4. Let's see them. They're gonna get crazier. Mode shape number 4. Then mode shape number 5. This is, you see, as I said, they get crazier, right? 1, 2, 3, 4, 5. This is number 5. So you get all of them. Number 6. Make it faster. You see all of these guys are still on one plane, okay? So this one. These are all potential ways that this can vibrate, this truss, right? So it's less likely for the last few mode shapes to get excited. Look at this one. This mode is gonna be the craziest one. Alright, so when you think about modes of vibration, it looks to us that it's much more likely to have this first mode happening in real life, right? This is much more likely. This one and this one. Let me show those two. These two are probably the most important ones, right? First two are very important. Number 3 was good one to look at it, re-look at it too. So let's look at, that one is likely too. Alright, so depending on the operating frequency, how the machine is working, those ones are gonna get excited, you see first two are very close to each other, but the number 3 is far away. Number 3, 4, as you move down, they're getting higher frequency. Alright, so let me do something. I'm gonna remove, just do an experiment. I'm gonna remove the constraint we put on the lines and see what happens. So to do that, I come here, structural, and displacement constraint we had on the lines, I'm gonna delete those. So all of them I deleted. Now let's run the experiment again, see how many this time we're gonna have frequencies and what's gonna happen. Alright, so I'm gonna come here, and for post-processing let me delete, by the way, or reset everything. Alright, so now let's solve it and see if we get let's say this time how many frequency the natural frequency and mode shapes we're gonna get. Okay, so I did it. So come here, result summary. Yeah, now we have 10. Okay, does it make sense? Let's see, in our we have how many nodes? 4 nodes, and technically we should have 12, right? 4 nodes, each node has 3 degrees of freedom in space, so we should have 12. The reason we don't have the last two probably is because the range, they probably fell out of the range I had defined. So let's test that, see if that's the case or not. So come here, analysis type, so option, oh yeah, okay, here's the problem. I said find first 10, but if I say first 20, I know there is only 12 of them, but so let's put 20, and then it's gonna find all of them. Alright, so let's solve it again. Let's see this time how many we get. Alright, solved. Now go here. There you go. We have 12 of them, right? So we have 12 natural frequencies now. Yeah. So some of them, early first four ones are frequencies are very small. Oh yeah. Yeah, the reason is because those are like rigid body motion. The reason is because this model, it's 2D and it's not constrained in Z direction. Does it make sense? I mean, there is no restraining force in Z direction. That's why first fours are very close to zero, and technically those are rigid body motions. There is no vibration in Z direction. This is, in other words, this is what I'm trying to say. So the reason those first four are kind of junk and close to zero is because this is a 2D member. I'm sorry, 2D truss. And in 3D, if you want to find natural frequencies, there is no resisting force in Z direction. That's why we have those junks at the beginning. So that's not a big deal. I just wanted to show you guys that when you increase the number of degrees of freedom, the number of frequencies are gonna increase. Yeah, those guys, first four are rigid body motions technically. So let's go, maybe let me see if we can plot them or not. See, go here. Probably we are not gonna get anything meaningful, but let's try it. So what did we get? Yeah, these are like 3D. Oh yeah, this is 3D. But as I said, since there is no resisting force in Z direction, those frequencies are small or close to zero. Technically zero. What is the reason? Because you remember frequencies are radical k divided by m, right? For 1 degree of freedom. So if there is no k in Z direction, right, then natural frequency is gonna be zero in that. That's the reason we have a zero frequency there. So radical k, there is no spring or no restraining force in z direction. I'm repeating, that's why frequencies are zero. Alright, so this is potentially this is one mode shape is z. The frequency itself is zero. Okay, so let me stop this and look at the other one, so at least we can see the mode shapes. Number 2, again this is a 3D one. It involves z coordinate. Do you see that? See this corner is alright. So and then let's look at it here. Number 3, this is another one that involves z coordinate. Alright, so another case. And then number 4, let's look at it. This one, let's see. Oh, this one is it? Yeah, this one involves, yeah, this one is a tiny number, again close to 0. There's another one that involves z coordinate. Yeah, so yeah, this one has z too. Alright, so then the next one is what we had before. Now we're gonna come to 2D. So when it comes to 2D, now we have the frequencies and mode shapes I already had after I had constrained z. Yeah, so the rest of them, the rest of remaining frequencies are what we saw before. Alright, so I just wanted to show you. So what we learned here, number of frequencies and number of mode shapes. It's gonna depend on degrees of freedom. You probably knew this fact, but we didn't try this on, we didn't look at this on like a truss structure like this. So we had here nodes that we had that they were free to move. We had 1, 2, 3, 4, 4 of them. In 2D they have 8 total degrees of freedom. So it means that in 2D we are going to find only 8 frequencies. And then in 3D, those 4 points, they have totaled 12 degrees of freedom. So we should be able to find 12 natural frequencies and 12 natural frequencies and 12 mode shapes, and we saw all of them. Alright, so at least now we have this guy confirmed. You know, this was taken from a paper, so we saw that works. Alright, so I hope you guys find this video useful.